which I'm calling, my name for them is Russian doll chain rule questions. You know those little dolls inside dolls? We did one at the end of yesterday. Remember the E to the X one? That's an example of it. The last 4 questions have chain rules where the question uses them multiple times. So a multiple chain rule question might be a more formal name for it. So I'm looking at this guy here, and I just realized I probably put more brackets than I need. There we go. If you're going to differentiate this, this is clearly a chain rule, right? It's e to the something. And so if you want its derivative, it's e to the something times the derivative of that something. Now, a lot of the time, this thing here, you just get the derivative with a power rule or a trig thing or whatever it might be, but not this time. Do you see that this guy here is actually a chain rule as well, right? It's a baby chain rule, right? It's a smaller one. If you want to differentiate the sine of x squared, the answer you get is the cosine of x squared times what? So if you differentiate the sine of x squared, you get the cosine of x squared times something. Times what? Sine of something, cosine of something, times derivative of that something.
2x.
2x. One of the most common mistakes that people make with multiple chain rules like this is that they lose the last one. They don't remember that the 2x is there, right? They kind of just do that, right? What you see, and they forget that extra bit. Now, the style rules for this are very minimal. You start with the simplest and you finish with the ugliest. So I'm not really doing anything, I'm just rewriting it in a slightly different order. So how about this one, which is a version of 23. Sine squared of x squared plus 3. And it's better to write sine squared, for some people at least, it's better to write it like that. This is that, right? It's just a different way of saying it. Now, when I write it this way, I can see the chain rule a little bit clearer. Would you agree it's something squared? So when you differentiate something squared, you get that to the power of 1 times the derivative of the something, the inside function. Now, if you want to differentiate the sine of x squared plus 1, it's a chain rule. It's the sine of something. So you get the cosine of that something, followed by the derivative of that something. To me, that's like, isn't it a Russian doll kind of thing, right? You got a big thing and then there's a little thing inside it and then there's a little thing, right? There's a big thing, a little thing inside it, and an even smaller thing inside that. And then you tidy it up. In this case, 2 and 2 get you 4. Then you do an x, and then the other 2 guys get kind of tied on after the event. So you probably won't have too much to do in the style point department, but you will have to be extra careful about chain rules inside chain rules. Okay, E ugly guy, sine of ugly guy. Aren't both of those going to need the chain rule to solve them? Right? E to the power of some ugly thing plus the sine of some ugly thing. E to the power of that guy, when you differentiate it, is e to the power of that one times the derivative of the sine of 4x plus Differentiate the sine of this guy, you get the cosine of this guy times the derivative of this guy. Okay, if you differentiate the sine of 4x, you will get the cosine of 4x, right? So if you differentiate the sine of 4x, you get the cosine of 4x. Times what? Derivative of sine x is cosine of 4x times what?
4.
Correct. The derivative of 4x is 4. And this guy is the cosine of e to the 4x, right? That's already done. The derivative of e to the 4x is e to the 4x also times a 4. Great. Now, all I'm going to do here is rearrange the furniture a little bit. So from simplest to ugliest in order, plus, I don't really know. What do you think? You think that's simpler than that? I think it is. So simplest to ugliest. I'm quite happy with the answer. If that was a test question, I wouldn't worry about it. Technically speaking, is there any style point that I could do to this? It's quite a minor one, and I probably wouldn't do it. Is there anything you could do in this expression?
Factor out of 4.
Yeah, would you agree it's probably not worth the effort because it's just as ugly with it as it was without? Now, if there was an e to the 4x in both of them, right? Just argument's sake, if there was an e to the 4x in both of them, I would pull that out, right? That's worth it, right? That's something useful. And we're almost done. I think there's got one. Oh, yes. Right, this is my version of 25. Y equals the sine of the cosine of the tangent of x. It's very similar to that e to the e to the e of the x thing, right? You got 2 minutes. You try it first. Do that, guy. And it's a treble Russian doll, if you need a clue. Okay, anybody brave enough to try this one? Because it's easy to get caught out.
I've only got the first one so far, but
I'll take what you've got.
Okay, I think it's cosine, and then parentheses cosine and then parentheses tangent x.
Correct. And then you would finish with the derivative of the cosine of tan x. So you did that bit right. So I'm just going to rewrite the first piece again because that's done. So doesn't our question now become finding the derivative of this guy? I should maybe give you a little bit more time to work on that then. So you're now going to have to figure out the derivative of cosine tan x. Okay, let's see if we can do the next level. So inside the Russian doll, there was this little Russian doll. So any volunteers for the derivative of the cosine of tan x?
Negative sine tan x.
Right, so differentiate a cosine, you get a -7, negative sine of tan x. Then don't you have to do the derivative of tan x? Well, right?
Yep.
Oh, we could probably do that one, right? Derivative of tan x,
Secant squared x.
secant squared. There's really not a lot I can do with this except try and make it pretty. So a negative, I'm going to do a secant squared x, a sine of tan x, and then finish with the cosine of the cosine of tan x. Right, don't need that. Right, that's it. Now, there are a million, literally millions of possible chain rules in the universe, and we've only like scratched the surface. So what you have to be able to do is understand how you do chain rules and not try and memorize a particular, situation, because there's just too many situations. You wouldn't be able to do it. So it's how you get the answer is more important than any specific answer. So we're now going to move. Oh, first, is there any questions before we do move on? Okay, we're now going to move on to our next section, and it's section 3.5. And it's called implicit differentiation. And this is a new thing, right? We're going to find out how to find slopes of tangent lines. That's all a derivative is in one respect, of curves that are written like this. There's a very simple example of an implicit function. I wouldn't actually call them a function, an implicit curve, because technically it's not a function, because for any x there might be more than one y. Do you recognize what that one would be if I drew it on my paper here? Anybody remember what x squared plus y squared equals 9 looks like? Pretty basic shape. Oh, you might have to hit the space bar because it was muted. Last chance.
A
Okay.
circle.
You got it. It's a circle. Do you know what the radius is?
Is it 3?
It is. So a very bad example of it would be that, right? So all the points that have the property that if you square their x and y and add them together, you get 9, make a circle, center of the origin, radius 3. If I choose any point on that circle, let's suppose I choose that point there, would you agree there's a tangent line? So it does, the derivative does exist. And I'm going to introduce you to some notation. Do you know that when we did normal, quadratics, that kind of thing, one of the common notations was y dashed. Right? Well, here's a new notation that also means the derivative. And the notation is dy by dx. So if you ever are asked to find dy by dx, you're being asked to find the derivative, right? It's just another notation. That's all it means. So dy by dx is equivalent to y dashed, which is also equivalent to f dashed of x, because don't you sometimes get it asked in that format, right? So they're not different things. They are the same notation, right? Different notation for the same thing. That's what I meant to say. So when you do implicit differentiation questions, you are going to be asked to find dy by dx. That's the notation that they're going to use, or the way they're going to phrase find the derivative. Now, there's a lot of skill building and little things that we need to do before we can actually start tackling finding the derivative of this function, right? Finding dy by dx. So let me tell you some of the rules. So I'm going to call it a term, and I'm going to say what the derivative is. Right. Now, if you have 5x, the derivative is 5. If you have 6x cubed, the derivative is 18x squared. If you have e to the 4x, the answer is going to be e to the 4x times 4. And for one last one, if you've been asked to find the sine of x, the derivative of it is the cosine of x. So what does that mean? It means if you are finding the derivative of terms that only contain x's, the derivative is the derivative it's always been. So for instance, won't the derivative of that guy be 2x? Now, when you have y's in your answer, like 5y, 6y cubed, e to the 4y, or maybe sine y, because that's going to happen. The derivative you get when you differentiate 5y isn't just 5. You are going to get 5 dy by dx's. When you differentiate 6y cubed, you're going to get, 18y squared dy by dx's. If you differentiate e to the 4y, you're going to get e to the 4y times a 4, but also a dy by dx. And if you do a sine y, you're going to get a cosine y dy by dx. And that comes from chain rule. If I said to you, differentiate 6 something cubed, wouldn't the answer be 18 something squared times the derivative of the something? In this case, isn't the something y, so times dy by dx. So you just remember that when you're doing implicit differentiation, it's a niche market. You don't do it anywhere else except here. When you differentiate anything with a y in it, you get the same rules with an extra dy by dx tagged on at the end. Okay, so that's the rule for doing these guys. Now let's put that together and show you how you find the derivative of this expression. Step 1. Just differentiate. Well, if you differentiate x squared, you get 2x. What do you get if you differentiate y squared? If you differentiate y squared.
2y.
Anything else?
dy dx, I think.
dy, but yes. So every time you differentiate a y, will you remember to finish with a dy by dx? Now, what do you get if you differentiate a number like 9? That's an easy question.
0.
You get 0. Now, normally when you do differentiation, don't you have the answer in front of you? That's not going to be the case when you do implicit. You have a step 2, and step 2 is solve for dy by dx. Because basically we're being asked to find what the derivative, what dy by dx is equal to. And we're going to use that technique that I call, as long as you do it to both sides, it's okay rule. So what I'm going to do is I'm going to subtract 2x from both sides. What should I do next to get dy by dx on its own? Right, so I've got this line. What would I need to do to both sides to get this guy?
Divide by 2y.
Agreed. And sometimes, and this is one of those steps sometimes, would you agree you can simplify it? So what I have got here is that the derivative of that circle is negative x over y. Now, if you tell me the coordinates of any point on that circle you like, right? If you tell me it's x and y coordinate, wouldn't I just do negative the x coordinate divided by the y coordinate, and that number will be the slope of the tangent line? Okay, I'll keep this here.
What does D mean? Is it?
It's, well, not a, it's a dy. It's the two things together. It's not d times y, it's a dy. It comes when you think of, remember when you did the tangent line thing and you did a little guy that looked like this? That guy is the difference in the y's, and that guy is the difference of the x's. And so the notation came from that. Know that a lot of you seem to have done physics, but don't you use a little delta symbol to mean the difference in x's and the difference in y's? You ever seen that? It's kind of connected to that as well. But we treat it as a notation thing. So dy by dx just means the derivative, right? Okay, right, let's try another one before we get into the hard stuff. So let's suppose I have a curve that's x squared plus y squared, take away 2x, plus 5y squared, minus equals 1. That is a really ugly curve, no idea what it looks like, but I can still find its derivative. So let's pretend that the question was, find the derivative. Find dy by dx. When you do implicit differentiation, which is what this process is called, your answer is always, almost always, x's and y's all jumbled up. So I'm going to take each one of these pieces and we are going to differentiate them using the rules that we've talked about over here. So if you differentiate x squared, you'll get 2x. If you differentiate y cubed, you will get 3y squared times dy by dx. If you differentiate negative 2x, you get negative 2. If you differentiate 5y squared, you multiply by the power, you reduce it by 1, and then you remember to tag on a dy by dx. And if you differentiate a number like 1, you get 0. So step 1 is differentiate all the terms. Now step 2 is solve for dy by dx. Now this question is a little bit harder than the first one, but as long as you do that rule, as long as you do it to both sides, it's okay rule, it should come in. So what I'm going to do right now is I'm going to subtract 2x from both sides, and I'm going to add 2 to both sides. So essentially what you try and do in these kind of more difficult questions is you try and get the terms that have a dy by dx attached to them on the left, and the things that don't have any dy by dx's on them, you get them over to the right. So here, added 2 to both sides, took 2x away from both sides. And dy by dx, right, this dy by dx and this one can be treated as a common factor now. And although there is other common factors I could have pulled out, like a y, don't. Only pull out the dy by dx. Right? So you'll pull that out as a common factors. So once you've done this, anything that doesn't have a dy by dx, get rid of it by adding or subtracting it from both sides. So the only things that are left here have a dy by dx in them. Then pull this out as a common factor. And there's one last line. What should I do to both sides to get dy by dx now, the derivative? Got this line. What should I do to both sides to isolate that?
Would you divide the 3y squared plus 10y?
You do. And if you can see any factoring or cancelling, you should do it. I don't really see any factoring and cancelling in this question that's worth doing. Would you agree? Nothing in the top has anything really that it can do with the bottom. And so we're finished. Okay, try another one. E to the x plus 2e to the y minus x squared plus y equals 4. And we are going to find the derivative dy by dx. Think of that as just a single thing. Don't think of it as a fraction. It's not helpful in this stage to do that. Just think of it as the derivative, right? It's y dashed, it's f dashed x kind of thing, right? Just think of it like that. Now, each one of these guys is going to get differentiated using the same rule we have here. Well, if you differentiate e to the x, you get e to the x. If you differentiate 2e to the y, you get 2e to the y times, remember to tag on the dy by dx if you differentiate anything that's got a y in it. If you differentiate negative x squared, you get that. This one might catch it out. What do you get if you differentiate y with respect to x?
One.
Anything else?
dy over dx.
So 1 dy by dx is just dy by dx equals 0. Are you comfortable with that? So differentiate all the terms with respect to x. You got this. Now, there are two different places, so agree here and here, that have dy by dx's. I'll cover them up now. Do you see that there's two terms that don't have anything with a dy by dx? So I'm going to subtract e to the x from both sides, and I'm going to add 2x to both sides. So subtract e to the x, and add 2x to both sides. Okay, we're 2 lines off getting the answer. Pretty standard thing you do next. You kind of do it every time. What do I do next?
Factor the dy and dx out.
Do it. And that leaves me with 2e to the y plus 1. And then the last line, again, it's pretty standard. You kind of do it every time. What do I now do to find dy by dx?
Divide by quantity 2e to the y plus 1.
And you should look for any tidying up, but a lot of the time, and this is one of them, you can't do much. We agree that's ugly, but that's as ugly. It can't be pretty, right? It's going to be ugly and it's done. And so we're finished. Are we getting a little bit more comfortable with this process called implicit differentiation? It's a very unique market, right? It's not y equals x cubed, right? It's some kind of function with x's and y's all jumbled up, right? You'll never mistake it for any other kind of derivative, right? Doesn't look like a chain rule, doesn't look like a product quotient rule, at least not now it doesn't.
So this is the slope of the tangent line.
Yeah.
Okay.
So if I had a point on the curve, let's just say for argument's sake that I had a point 0, 2, right? That was on this curve. Then if you found dy by dx, it would be negative e to the 0 plus 2 lots of 2 divided by 2 lots of e to the 2 plus 1, and that would be 4 take away 1 is 3. Can really do much with that. But that number would be the slope of the tangent line to that curve, right? So whatever 3 over 2e squared plus 1 is, that would be the slope of the tangent line at 0, 2. Can you just pretend that I knew what the shape was, right? And if I picked the point 0, 2 and it was here, well, let me pretend it's here, that tangent line would have this slope. The only people, and I'm not even sure if Desmos can cope with it, but most of these curves are almost impossible to imagine. You know, I can imagine y equals x cubed, right? I've seen enough of them in my life. But would you agree that there's no way in the world you can really tell what that looks like? Implicit curves tend to be weird things at the best of times. They look like peanuts. Some of them look like spirals, you know, depends on what they got. Now, I'm going to do one more of that type, and then I'm going to introduce another level of complexity that we haven't dealt with yet. So this is one more of this type. So it's going to be 3 cosine y's, take away 2 sine x, plus a y cubed equals a y. Now, I did a little bit extra that I hadn't in the other two. I'm not going to change really what I do. If you differentiate 3 cosine y's, you'll get negative 3 sine y's. Remember to finish with a dy by dx. Why? Because this is a y. Differentiate this guy, you get negative 2 cosine x's. Differentiate this guy, you get 3 squared times dy by dx. And differentiate the y, don't you get 1 dy by dx. So what's different here is I've put a situation here where there's now 3 dy by dx's, right, instead of 2. And secondly, isn't one of them on the wrong side? Right, they should all be on one side. But we can fix that because we have a rule that I call, as long as you do it to both sides, it's okay rule. And now I'm going to use it. I'm going to add 2 cosine x to both sides. And I'm going to subtract a dy by dx from both sides. And when I do that, so I finish writing this down, We get that? Are you comfortable with that line? That I added and subtracted things from both sides so that any term that had a dy by dx attached to it ends up on the left, and anything that didn't have one ends up on the right. And basically you add or subtract, in this case, add to it cosine x's, in this case, subtract 1 dy by dx. And then you pull out the dy by dx. And you finish with dividing. And that is the answer. Don't expect too many pretty answers in these questions. You agree all the answers we've got are for the most part pretty ugly. So you won't get much in the way of style points because of that. Any questions about what we've done so far before I add another level of complexity to the situation? You feel comfortable about how you tackle the ones that look like this at least? Right.
Where did the -3 go for the -3 sine y? Does that go where, or was that just a typo?
It's a typo.
Okay, just making sure I didn't miss something.
No, glad you found it. Other people would probably look back and wonder why I'm doing it as well. Anything else? So we good? Right. I got these guys. If the thing's got an x, the derivative is what it was always. If the thing's got a y, isn't the derivative what it always was? But you remember to add on these guys. So now what we're going to look at is, what do you do when one of the expressions is that guy? Right? You've never seen this before. Right? This will just be one piece of the puzzle, right? There are other stuff. But let's focus on what you do about just differentiating this. Now, you notice that both terms have a y in it, right? What do you think you would do here? Any guesses?
Would it be the product rule and then you just use by dx?
Yeah, it would be a product rule. And so what you would do is you do f dash g plus f of g dashed. Now, if you differentiate y squared, you get 2y times dy by dx, and then you leave the other guy alone, plus you leave the first one alone, and if you differentiate e to the y, you get e to the y times dy by dx. And all I'm doing here is rearranging things a little bit. And I'm not going to do any style points or collect like terms or anything, because you would do that later, because this isn't going to be the only piece. There's going to be other stuff going around it. So if you have a situation where both terms are multiplied and both terms have y in them, don't you use a version of the product rule? What do you think you would do if one of them was an x squared and the other was got a y in it?
You would still do the product rule, but then only the x squared e to the y would have d to the y would be the x.
Yep. You do a product rule and differentiate this guy, you just get 2x, right? You don't get anything else because x squared is 2x. Leave the second one alone. Leave the first one alone and differentiate this guy. Now you look at the two answers, they're not identical, agreed, but would you agree they're similar? Because aren't you doing similar things? So the back of your mind is the only real major rule you need to keep track of is if I differentiate a y, anything with a y in it, make sure you finish with a dy by dx, right? If you stick to that rule, you can do all sorts of weird functions. Here's
So
the
the
difference.
d
Mhm.
oh
Yeah,
the,
you were
the
saying?
dy in dx, it doesn't go on with the exponent with the y is like separate. It's not the exponent with it.
Well, I'm not sure. I mean, these things are multiplied, so they're all separate, if that's what you're asking.
Oh, okay.
Now, what do you think? That's pushing it, but I mean, it could happen. You don't need to tell me the answer, but what process would you use? Product rule, quotient rule, chain rule? What do you think you would use as a process to differentiate that particular term?
Chain rule.
And the chain rule says the sine of something is the cosine of something times the derivative of that something. Well, if you differentiate y squared, don't you get 2y? And always remember to finish, the last thing you write down is your dy by dx. Does that make sense? That's how you would deal with that if it happened. So if two things are multiplied, use the product rule. If it's a chain rule, use a chain rule. All you worry about is, or need to worry about, is make sure that when you're finished, that there's a last term is a dy by dx at the end. Are we good? Right, I'm going to show you something right now. So while I'm getting myself organized, why don't you say your last name for attendance? And I will show you in a few moments because I'm just basically loading it up. Still some people put your last name down, guys. I only have 12 here. That's a bit better. Right, that's it. Right. So you should be, I hope, looking at our classes Canvas site. And there's a guy here at the top called Midterm Exam Information. Now, if you are not doing it, we don't have enough time, but you can do it in your own time. If you click on that one, there's a PDF that will basically tell you how the test is going to run. You know it's on Monday. You know that there's 2 time slots depending on what fits your schedule. So in our case, I believe it's 11 till 1 p.m. or it can be, was it 11 to 1 and 12 to 2 p.m. Yeah. I've also decided how I'm going to organize the content. It's in chronological order, which I was always going to do. So the first question is week 1 and the last question is kind of what we're doing today, right? That kind of thing. Also, there are going to be 10 multiple choice questions where you're given a question and there's 4 or 5 possible answers, but only one is correct. In the multiple choice questions, pick a letter. I don't want to see working. I don't need to see working. It won't change the answer. So you just say question 1 is C, question 2 is D. And then there's going to be 10 section 2 questions, all of which are going to be on Canvas, nothing on WebAssign. And those are going to be just like we've been doing today, you know, differentiate that, you know, find f dash of a, all the things you've been doing over the last 5 weeks. But those I do want to see working, right? Because if I don't see working, I'll assume that you're not doing them correctly and you're just doing shortcuts that I don't want to see. Now, if I click on this one, and it opens up, this is the link to the midterm exam Zoom meeting. So don't use your class link. We have a special one for your midterm. And that was it there. When you're finished your test, you have to upload your working. And what I have here is these are links to get the program. This is Apple phones, this is Android phones. Here's a little video that shows you how to use it. And essentially you take pictures of your written work and this software will turn it into a PDF and then you can upload it. And right now I've got a little guy called Practice Uploading working here. So if you've never done it before, you can play about with it and try uploading things. If I click on it and I go to Student View, What you do is you hit the red button, start assignment. If you've saved it on OneDrive, you click on this. If you've saved it on your computer or on your phone, then you leave it as that. You go choose file, and you go hunting for it wherever you've stored it. You pick it, and you say open, and then you submit. And that's it. That's how I will get your working. So you'll get your phone, you'll take pictures using the software that I've mentioned earlier. Now, you don't need to use the particular software that I said. I've got Microsoft Lens, it's free, you can use it. Some people, because their English class did a different thing like Cam Scanner, use that. Some of you are old school, you can stick it through your printer and scan it. Right, as long as I can get it, I'm happy, right? And I think I have, yes, I do. If you click on this one, what I have here is a practice. So you can get an idea of how I ask questions and what they look like. So here, for instance, is some questions that refer to this diagram. So if I went and said to you, what is the limit as x tends to 5 plus, so that's a right-hand limit, the answer would be 4. And if you believe that was the case, you would just say 4. So all I would see is C. So 1 would be C. And here are a load of questions. And here is section 2. Well, can anybody remember what technique you use to find a limit that looks like that?
Conjugate.
Conjugate. In fact, isn't this one here also conjugate, right? And the other techniques are factor and cancel, which I would use for this one and probably that one. And as I scan through here, there's a whole load of stuff, and there's the solutions. And this is just a resource for you, so you can choose to look at it or not. But it doesn't mean, for instance, this guy here is what we're doing right now. Right? This is implicit differentiation, just to give you an idea. It's a resource. You don't need to use it if you choose not to, but it does give you an idea. And what I was saying is, if I haven't put a particular type of question in this practice, that is not an indication that it's not in the test. Or that if I have a question in this, that's an indication it will be in the test. This is just give you a flavor, some things, some of them bound to be in the test, right? You know, I'm bound to give you a product rule. Would you agree we've done enough of them that it'd be amazing if you didn't see a product rule or a general, right? But there are other things we might not have done quite as many, and they might not appear. There is a rule that I have is, you know, if you only know half the stuff or you only study for half the stuff, isn't the half you didn't study the stuff that's in the test, right? So if you had 10 topics, but you decided to focus on 5, isn't Murphy's Law going to be the 5 you didn't study or the ones that are in the test? So you gotta just be, if you're ready for everything, then I can't surprise you, right? You're going to be able to do any question. And that's the best advice I can give. Right, any questions about what you've seen? Otherwise, it's bye-bye.
Do you say how many questions the exam is going to be?
Yeah, 10 multiple choice. Multiple choice questions should take no more than 3 minutes. If they take longer than 3 minutes, pick C because you're wrong. Whatever you're trying to do is not the way to do it, right? And I don't want to see, I'll just repeat myself, I don't want to see any working for those. So all you will write down in your piece of paper that you'll take pictures of is 1 is A, 2 is B, 7 is C, right? That's all I will say. Section 2, 10 questions as well, but I want to see working. If I don't see working, you're getting nothing. Because you could, who knows what you could have done. It's open book. Anything you've physically got written down, you can use. Right? Any formulas that you've got, anything like that, you're allowed to use it. Calculators are allowed. Desmos will be there for you as well. Any other questions? Bye-bye, guys. I'll hang about in case there's a single question that somebody just wants to talk to me about.
I do.
Yes, what you got?
Okay, so I'm just making sure I'm clear. So we're
Mhm.
looking at me just writing my answers on notebook paper and then scanning the notebook paper in and then uploading.
Yes.
Okay, and then is there going to be, so in order for me to upload it, I'm going to have to stop the Zoom when I'm done and then upload it and start the
Yes.
Zoom.
Yes, but
Okay,
you
okay.
know, that won't take that long. So you'll have finished the test by then. So I'm assuming that you won't do any last minute change and you'll have it uploaded.
Okay.
It doesn't take that long to do. In fact, if you're using your own, as I am, camera, you don't need to switch off Zoom because you can take pictures. And it's
Right.
only the last minute that you would actually need to do it. What I want you to do is tell me when you're finished. So don't leave, because I will go in, and if it's uploaded correctly and I can read it, I'll say, you're good to go, Rachel. Because sometimes you might think that you've done it right, and a garbled mess appears, right? And I can't see it. And I'll say, hey, you might not have done that right. You want to have another shot at it, and then I can tell you it's good.
Okay, I'm not going to be able to do it with a phone. I will have to disconnect. There's only one USB
doing a
port.
scanner?
I have a printer scanner.
Right, that'll work. In your case, you probably will do exactly what you said.
Okay.
Well, I'm
I
not sure.
will-
Okay, your printer can, yeah, you can close a window and still have everything on apart from that. You could do it that way.
I have to disconnect the school's USB hotspot in order to upload the file through the
Oh,
USB port. There's
okay.
only a single port.
Okay,
And
you
so
can only do
that's-
one thing at a time, and one of them's
Yeah.
being used. You have to take it back out. I gotcha. But not a
Okay.
problem.
Okay, I'll do it as quick as I can.
Right.
So,
But remember
okay.
when you finish to come back in to Zoom and say I'm finished so I can double check for you.
Okay, it'll let me come back into the Zoom meet.
Yeah,
then.
you can go into Zoom and back out of Zoom as many
Okay.
times as you like.
Okay. All right, great. Well, thank
Okay.
you.
Right. Any other questions? Teresa, Natalie?
I just had a quick one very fast before you have to go. There was one on the homework that I just wanted a
Okay.
quick walkthrough.
Okay, what you got?
It's y equals x squared times e to the negative 6x.
Okay, so that's going to be a product rule and a chain rule as well. So it's going to be a kind of a bit of A and a bit of B. So
Okay.
here goes. I'll call this F and I'll call this G. So the derivative is going to be the product rule. If you differentiate that guy, you get 2x and you leave this one alone. If you leave this one alone, and then you differentiate e to the negative 6x, that is actually a little baby chain rule. It's e to the something times the derivative of the something. So what you've got is 2x e to the negative 6x, take away 6x squared e to the negative 6x. And then style points. I'd pull out a 2, an x, and an e to the negative 6x. And that would leave me with 1 minus 3x. Did you forget that little negative 6? Because that's the most common mistake people make.
I think I'm just struggling a little bit with the chain rule concept.
Right. So when you're looking at this guy here, think of it as e to the something, put a little asterisk. And its derivative is e to the something times the derivative of whatever that something is. So in our case, it was negative 6x. So you get negative 6x times the derivative of negative 6x. And that's where this came from.
Okay. Times derivative. Okay. Thank you very much. I appreciate it.
Not a problem. I'm going to have to, Natalie, unless it's a really quick one, I have another class I should be in 30 seconds from now.
Oh, I can just ask you tomorrow. That's totally okay.
Okay. Office hour is 10 o'clock, or catch me, before the class starts or whatever, if you don't want to wait behind. Okay.
Sounds good.
Bye.